Hi everyone, my name is Esfandiar Kuhi and I'm Simulation Product Manager Technical at Intercad. Today webinar we are talking about Solidworks Simulation drop tests versus dynamics. Okay, what we are trying to achieve in this webinar is to introduce Solidworks drop test definition and capabilities and limitations. We start to practice drop test analysis within a case study, which is falling off a camera on a rigid floor. We will learn how the drop test setups and list of inputs. We are going to the result and recording options, and we compare between the different impact testing in our case study. And at the end, we will go and review the limitation of drop test. Now, in the second part of our, let's say, presentation, we will introduce an alternative solution to drop tests, such as linear or nonlinear dynamic studies of the same model. Well, we are introducing, let's say, dampening factors. We'll review the inputs and setup in linear dynamic studies and finding the best time resolution to record the results in a nonlinear dynamic study. And then at the end, we are comparing between the different impact testing in nonlinear dynamic as well. So what we're trying to achieve is to see how drop test is working, what are the limitations, and as a complete solution, how a linear or nonlinear dynamic studies can, let's say, resolve the similar sort of problem. All right. Before we go into the case studies, what we would like to highlight is the seats of simulation SolidWorks, and we understand where we can use the drop test and then where we can use the linear or nonlinear dynamic. Well, if you have a look, we're starting with SolidWorks Simulation Standard. Well, we can do a linear static assemblies and components and parts. We can do time-based motion and fatigue studies and trend tracker. So the next upgrade will expand the application range by considering frequency, thermal, event-based, buckling, optimization, 2D simplification, submodeling, and edge weight collector. Well, that is all stay in the, let's say, linear and static, let's say, application. And the only one which considering nonlinearities in terms of material and time integration is drop test. Okay. Now let's go and define what is the drop test look like. The drop test study is a specified type of dynamic analysis used to model the impact force of a short time duration event. When we're saying about dynamic, means the force and let's say displacement are changing with time. And when we are introducing impact force, this impact could be on a component or an assembly where we have a rigid or flexible planar surface for the impact. We're basically going to an explicit method of direct time integration to solve the problem. The benefit of this scheme is numerically very stable technique for a small time step, but it could be computationally very intensive. All right, with that explanation, let's have a look to our case study, which is a drop test analysis on a camera. So as you can see in a slide, we do have a camera with 4 components: top cover, bottom cover, lens, and zoom area. It is going to drop from a height of 2 meters on a planar surface. The first case study, we will consider a rigid floor. All the components are bonded, means they are basically treated as one part, not really an assembly. And we will look at the response. Then on the next case study, we will modify our floor to be flexible, basically a nylon-based floor. But still, it is a fully bonded component and one single part. And the third case, we're considering a rigid floor, but this time we will consider plasticity, means if the camera's let's say components is failing, we are considering the permanent failure on that part by considering an elastoplastic material, but the actual thing is fully bonded. And then the next case, which is case 4, we have a rigid floor, but this time we are treating our model as an assembly. Means we do have no penetration on components. All right. To have a very quick overview about inputs in drop test, what you can do, either you consider a drop high or a velocity at, let's say, impact. Then you should specify the velocity magnitude of drop high here. Then you are going to get the gravity magnitude and orientation to the software. And then you are specifying the target orientation. So either it could be normal to gravity or parallel to reference plane. Friction is what you can include, and at the end you are going to introduce the stiffness of the impacted surface or wall. So either it's rigid or it's a flexible target, and you would like to enter the axial and tangential values of flexibility. All right. The other thing we have to mention about drop test is how we would like to record the result. Result in the, let's say, drop test is our observation of time. For how long after impact should one observe or capture the solution? SolidWorks basically, based on the geometrical calculation, is simply coming with an initial value for you. Well, in this case of camera, it's been recommended for 50 microsecond. That preset values is based on model geometry, material properties, and the elastic wave propagation. But basically, the time is 3 times L, the highest length we have, divided by nu, which is elastic wave propagation, and it is highly dependent on elastic modulus of the material and density. Well, since you have specified your time of impact, and then you are going to how many plots you would like to record the result on. So right now you can see 25 as an example is shown in this figure. Okay. One extra thing you can always do that is to define sensors on the location that you really like to record your result on. For example, you can see in a zoom area, we have 4 vertices to record our result. Therefore, we simply can trace the result of any kind stress, strain, or displacements on preset locations. Okay. Now let's go to the case study and start having a look. Alrighty. So let me bring the camera model, and here it is. So as you can see, if we go to the model tab, we can see we have bottom cover, top cover, zoom area, and lens area. Alright. And then from this point, what we can do is simply start a new study. But before that, I have to tell you guys, SolidWorks Simulation is look like an add-in. An add-in, the simulation add-in can be activated by ticking off this box, and you will get the simulation tab here. Doing so, then what we need to do is to simply create a new study. And by creating a new study, you can see the range of studies we can do here. And one of them is drop test, as you can see here. Give it a name, click OK, and you're creating the first one. Well, basically, we're following up the same steps as we do with the other type of simulation. We got our parts with list of components. Any of them could be excluded from the analysis if you like, but generally we have first to apply the material to them. So either applying material to group means apply material to all, or if you're going for your favorite material, or select the component to apply the material on it. All right, so as you can see, the bottom cover, top cover, and zoom area are using magnesium alloy, and lens is using glass. Looking at the material property, it's all about linear elastic isotropic material, and there is no other plasticity models being considered here. All right, so that is the first thing we have to do. Next, we are coming to a selection of contacts, well, we have bonded contacts with all components. So a global contact set on a camera assembly and with a compatible mesh through all the components. And then we are ready to start setting up the drop test. With that one, we have to edit define, and here is the menu section as I've introduced in the slide. Drop height, 2 meter. According to horizontal plane, we have the gravitational for, let's say, acceleration of 9.81 meter per second square. The target orientation is normal to gravity, and then we have a rigid target. Well, you can see the camera model is going to fall on an angle. That's how the geometry is being built. So you either can go for impact velocity and then face or edge for direction, give it a magnitude, and then repeat the same thing as gravitational, let's say, effects, and also the target stiffness and orientation. Well, we accept it with 2 meter high, and that's all what we need to do. All right, so from this point, the next thing we have to do is how we would like to record our result. So by right-click on Result option, go Define Edit. This is the recommended value based on the geometrical calculation and elastic wave propagation, which is 50 microsecond after the impact. We're saving the result for 25 plots, and here is what we record. All right, now we are ready to run the case. So in order to save the time here, guys, I have run the case, and you can basically look at the results. Beforehand, I introduced the result. You know about the sensors, and I have set up a sensor. Basically, you can go to Evaluate tab, click on the sensor, and ask for creating a sensor type such as mass properties, simulation data, dimensions, interference detection, measurement, proximity, close data, costing data, or motion data. So that is a sensor can be used in a various sort of, let's say, studies. Well, this time we definitely need the simulation data, or we're going for workflow sensitive, and we have 4 vertices to trace. 1, 2, 3, and this time 4. That is what you're supposed to do before you're running the studies, and exactly is what you can see here. Simulation data, workflow sensitive, all these vertices as you can see in a list. Now when you run, you are able to look at the result at specific points for any properties you like. All right, now let's look at the result. This is the stress result. Well, as is expected, we do have some stress on the impact, which is very high magnitude for sure. Just letting you know that might not be in reality because, one, we are considering everything fully bonded, and there is a highly stiff, let's say, imaginary target to impact. Stress values are showing around 1,193 megapascal, and there are some concentration and singularities on the corners. Also for the displacement, you can see how does it going to displace. Let's do the animation and having a look. So the camera is falling down and stress is simply getting propagated, and different parts and different regions are, let's say, deforming variously. All right, now what is very important for us, and that's why we have set up the sensors, is to trace them on our location. So if we go define time story in any of these vertices or all of them together, we can ask to review the stress, displacement, translation, or translational acceleration and time as one axis. Then by clicking OK, you're creating your response graph as I'm showing you in a minute. So basically it is showing us how the stress get change over 50 microsecond after the impact for all these locations. So it's quite high stress values you can see on the first node, and the other one is much less after the impact is happening. Now, we are not going to analyze the result for this time, but what we are going to do is to make these cases more close to the realities by considering, let's say, a flexible floor or making an assembly with the contact between the components and look at the stress values there. All right, so this is the basis of drop test, how we set up and how we record the results. Now let's move to the second case study. Well, this time I'm simply creating the same thing by right-click and duplicate your study and give it a name as you like to do. And the only thing I would like to change here is to simply go to my setup and change the target stiffness to be flexible and give it a value for normal stiffness and tangential stiffness here in your selection. Well, how we calculate and let's say getting these values is a different let's say topic. We can provide you solution if you are not 100% sure how to get these values. Please contact us at any time if you like, and we simply provide you the solution for that one. But for now, you can see I have put the values of normal and axial and tangential stiffness to the box. That simply means this time, instead of having a rigid floor, I do have a nylon-based floor, but still my camera is one part and everything is bonded. Solving with the same setup and recording results, let's say parameters, I can see my stress values is considerably changed with this top maximum, and still I can see singularities on the corner and the let's say surface of impact. Well, what is very important for us is to look at the response graph here in our simulation. Well, you can see again in all these four nodes we have very considerable drop in the magnitude in top magnitude of stress are down to around 50 megapascal, but it's happening on the same node. Good. Now we are trying to make the case as close to the reality. That's why I'm going to have the third case study. Well, this time, as we know, when such a impact is happening, we have some permanent deformation, or let's say one of the materials are going to permanently fail and we have plastic deformation on it. Therefore, the material should be modified to capture the plastic deformation on the model. And now if we have a look to magnesium alloy here, we have created our own material and with the values as you can see here, but this time instead of linear elastic isotropic, we do have plasticity von Mises. Means we are going to have a count of permanent deformation on the structure and look at the stress redundancy after the impact finish. All right, so this is the change I've done and same setup. This time I'm again getting back to a flexible, a rigid floor and same drop high. Now having a look to how much permanent deformation we might cause. Looking at the stress values, then we can see we have 242 megapascal of stress generally recorded. Well, if we go to edit definition, you can see this is the maximum happen. However, this time we can go for any time step and look at the stress values there. So at the first 1.99 microseconds, which is the first step, we recorded 159. So increasing the time, and we can see how the stress has been developed. You always can ask for the maximum values across all the steps, and by clicking OK, you can see this is when it's happening. 242.213. Looking at the animation, let me activate, click OK, and look at the animation of this one, hopefully. Hang on a minute. Displacement. We can do animation, stress, not. All right. So let's look at animation on displacement. You can see still we do have stress propagation after the impact through different parts. All right. Now we understood we progressively reducing the top values of stress either on specific location we are looking at in a drop test when we are considering more and more reality, like there is not super stiff target floor, or if we have, let's say, a plasticity in our material. Well, you can considerably see that the maximum stress is reached somewhere around 30 microseconds, and after that it's dropping down to any other values. As you can see, most of the nodes are simply dropping down their stress values down to around 80 to 60 megapascal. All right. Now let's go to the last case, which is freefall with the contact. This time I have set up a contact set between top and bottom cover, this face and that face. Well, it is no penetration. Now I do have an assembly. Although we have multiple parts in the other studies, this time we do have an assembly because there are two components which are not glued or bonded or welded together, and they can act separately. Rest of the study, as you can see, the setup is the same with the rigid target. Now look at the stress result, and you can see a very, let's say, important magnification. Very high stress, since these two components can act separately and they have a contact, we have a stress concentration and very high stress concentration at their contact area. Also, as we expecting, we have the stress singularities on impact, that is expected, but since these two components can be separated, we see the stress. Well, that is a considerable information to consider for designing this, let's say, snap-through assembly feature. Looking at the displacement, we can animate this time with freefall, and now we can see how the camera is falling down. Well, it's better to have the displacement values to be automatically magnified, and let's look at the animation this time. So you can see when the impact is happening, we do have a misalignment between top cover and bottom cover here. And same time, if we have a look to response graph, we can see the magnitudes of stress on 4 predefined locations. Yes, the stress from 0 up to 50 microsecond is going to increase and have a bit of vibration. But the top magnitude is around 180 above down to 130 in different locations. Well, what we do have in all this study is to trying to make more and more close to the reality case. Now looking at the summary of what we have presented here, you can see the first case study which we considered a rigid floor, our top magnitudes of stress has been recorded around 400 megapascal on one point, and the other points are also, let's say, starting from 150 down up to 350 here. One basic assumption, which is just, let's say, a flexible floor, can reduce the magnitude of top stress down to 88% here. So it is very important if we are going to test our, let's say, product for the impact test using drop tests, the rigid or flexible floor, when in reality has a major impact on the, let's say, stress result, is also getting appear here. Now with two other alternative, either it is elastoplastic material, means we have deformation and permanent deformation here in our assembly, we can reduce down to 70% of let's say magnitude of let's say stress, and you can see this node, which is 47229, was the highest stress magnitude recording. Well, that is an alternation, and the other node is coming to be on top. So not only the magnitude of stress is changed, but also we have an alteration on the highest stress point. So it's absolutely different perspective of the result here in our simulation, just considering the plasticity or non-linearities about the material. Well, look at another fact and another reality in our case. If we have real assembly and we have contact on different, let's say, components, we definitely can see the reduction in the top stress value, which is very, let's say, conservative, let's say, case in a rigid floor, and also same alteration with the maximum point at the same time. All right, so all these cases study with the drop test, what it's trying to show us, we have to be more and more close to the reality to look at the correct stress value. But one thing for sure we have missed here, and that is a wrap up about what is the drop test analysis limitations. Well, basically, you know, when we have such a this study, we're trying to find an equation, let's say equilibrium equation of force, which is initial force, dampening force, and elastic force should be equal to gravitational force and impact force. That is what we're trying to solve and bring to the equilibrium. Well, definitely in a drop test analysis, what we don't have is dampening. Therefore, one important factor from our study is getting neglected. Also, as we saw and experienced within the case study, we can't define any sort of load or restraints, like as pressure, force, torque, or anything else. That is just restricted to the drop height and gravitational effect. These sort of studies are not performable on a shell, beam, or truss elements, or even composite material. We're just considering nonlinearities in one scheme, which is one misses plasticity. Therefore, the range of material we can do such a this analysis are very limited for those who one misses plasticity constitutive material is true. Therefore, if, for example, you have a rubber type material, which is a hyperelastic material you have in your model, you can't really perform a drop test. And we saw it when we were setting the contact, let's say, the drop test setup. There was a contact dampening. This is not a real contact dampening. It is just a multiplier, which is simply providing a numerical stability, and it's not a real dampening. So when you have any energy imbalance occurs, you are just going to, let's say, giving some stability to your numerical scheme, rather than really solve the model in a correct way. All right, so we understood what drop test can do for us, and what are the limitations, and what we can achieve, and how we close to the reality is simply giving us the correct answer. Now from this point, I would like to move to the next package we do have in SolidWorks Simulation, which is part of SolidWorks Simulation Premium, Linear Dynamic and Nonlinear Dynamic Studies. Okay, let's go and find a bit more information about this type of analysis. A dynamic analysis used to model the impact force of time-varying load on the structural response of their product design. We can ensure the performance, quality, and safety by doing such a this analysis. We can incorporate frequency, impact, and dampening in this type of a study. And when we are using this, is basically if we're running a frequency analysis and finding if the frequency of the load is larger than 1/3 of the lowest or fundamental frequency, the dynamic study needs to be taken. We have two different methods to, let's say, take the dynamic study. One is linear modal analysis, will be determine the natural modes of vibration, and then displacement, stress, strain, velocities, and acceleration are getting computed. And the nonlinear dynamic, let's say, analysis, well, we are calculating displacement field in every time step, given the applied loads and initial component velocity. What we get from this field is the nonlinear stresses, strains, velocities, and accelerations. All right, now it's a good time to focus on the dampening. Well, we introduced this is the lack in drop test analysis, and this is what we have in linear and nonlinear dynamic. Basically, dampening is a characteristic or capacity of the structure to dissipate the energy due to the various phenomena. Well, it is quite natural. If you are hitting an object, it's going to vibrate, and this vibrate is going to dissipate because of the dampening. And this is exact fact we have lost or missed in our drop test analysis. This phenomenon is really difficult to measure or characterize. We are usually taking, let's say, experimental tests to understand the, let's say, vibration and, let's say, dampening ratios on our structures. We have three types of dampening in reality as a major, let's say, category: viscous, clump, or frictional, and material. And then just letting everybody know that dampening in Solidworks simulation is just considering viscous type here. The other two are simply converted to the viscous based on the, let's say, principle of equivalent of dissipated energy. So in SolidWorks, we just having viscous dampening factor. Now, if we're looking at the dampening and viscous on a single degree of freedom, let's say, system, the magnitude is proportional to the velocity and the vibration of the structure. Well, basically F equal to C V in a power of n. We can characterize dampening by dampening constant of C or dampening ratio of zeta, which is the ratio between dampening and critical dampening. And the critical dampening is simply related to stiffness and mass properties. The other model which we are using in nonlinear dynamic studies is the Rayleigh damping, and this dampening is also related to the mass and stiffness with two constants of alpha and beta. They can simply get connected to zeta with the given formula. What is very important to understand is C and zeta, or a pair of alpha and beta constants, characterize the same viscous dampening properties. We're mostly using dampening ratio of zeta in our calculation in SolidWorks. So either we go for a constant dampening factor or we go for a Rayleigh damping. This is where we introduce the dampening into our dynamic studies. There are lots of other, let's say, factors and measure of structural dampening, such as low loss factor of the system, specific dampening capacity of the system, logarithmic decrement of free vibration on the system, as you can see in the formula, and the resonant amplification or quality factor. The other measures, such as revibration time, phase angle, attenuation of the plane bending waves, attenuation of plane longitudinal waves, and the all other factors, is simply wrapping up the case. The characterization of dampening is very hard, and we mostly getting those values from the testing. So either a resonant beam testing, as endorsed by ASTM, or dynamic mechanical analyzer testing, resonant TENS, or other tests exist. For those who really like to be interested on this, we can provide more reference for your review, but mostly we have to conduct the test or go to the literature and find the dampening, let's say, ratios for the structures we are, let's say, thinking to design. All right. We have this brief introduction to the dampening. Now we would like to repeat the same test on the camera. This time we're using nonlinear dynamic analysis. The camera is going to hit to a physical target floor, fully fixed, either it is fully stiff or it is flexible. We have no penetration contact set between these two components. And in order to resemble the 2-meter high, we simply converted the height to impact of velocity of 6.25 meter per second. The first case, we will have a linear dynamic study to understand the modes of vibration. We look at the highest frequency and mass participation. This is a very good guideline to understand the natural frequency and if the dynamic studies is applicable, and find out the resolution of the time recording and the minimum time we have to, let's say, solve the model. Second case, then we start setting up a nonlinear dynamic study. We have a stiff floor, fully bonded components, and no dampening. That is a very good case comparison between what we have here in dynamic and rigid body floor in, let's say, drop test studies. In the next case, we will start making our test more close to the reality. We have nonlinear dynamic case with highly stiff floor, fully bonded components, and Rayleigh damping. We simply bring dampening effect and look at the considerable reduction in stress value. And in the fourth case, we will make everything as much as close to the reality. We have stiff floor, no penetration, and Rayleigh damping. So we considering nonlinearities of the material, we considering dampening, and we considering geometrical nonlinearities and contact nonlinearities in our model in case study number 4. A quick overview about what we do. A linear dynamic test or frequency test could be performed on this structure to look at all the frequency, natural frequency from mode 1 to mode 10, understand their, let's say, shape, and look at the mass participation in each direction of impact. Also, based on that, we can look at the time such as these frequencies are occurring, such as period you can see here. Usually, we are not going over around 5,000-6,000 hertz of frequency. This is highly, let's say, impossible to occur in the model. So basically what you need to do is to look at this frequency, which is happening in mode number 3, and look at the period of its happening, and basically you have to go and divide this by multiply it by 0.1 and get your recording result time step. Means you are going to perform for 50 microseconds while you are simply recording result at this time step divided by 10. But as a conservative, let's say, method, we are simply performing a linear dynamic test. We're looking at the mass participation factor until we reach at least 80%. And if it's happening on the mode number 10, then this is the time should be divided. But as the reality, and that could be very, very, let's say, tiny time steps to record and may take a lot of time, that is better to stick to the other rule of 5,000 or 6,000 hertz, look at the period, and record on the scheme of 1 to 10 to this period of time. All right, now let's get back to our case study again. Now here, that's where I've created my first nonlinear studies. Same procedure we have to take is basically we going to simulation. Looks that we have some problem here. If we have to rebuild, and yes, I have to activate this configuration. Well, I do have multiple parts, same camera parts, and there is a target as a hit ground. and we got magnesium alloy still for that target, magnesium alloy and magnesium alloy here again. So all treated as linear elastic material, and now we are ready to do the setup. All right. No damping, and you can see the contact set. No penetration between the camera and target. The rest is using global contact set as fully bonded everything here. We have fixed the back of the target, and then we can simply apply an initial condition. So you can see I can apply initial condition to a specific, let's say, assembly component or face. According to horizontal plane, I do have 6.25 meter per second as a velocity of impact. So the camera is going to hit the target at that speed. All right, so inserting a boundary, let's say initial condition, is also we activated the gravity, 9.8 seconds, and we simply using the same mesh. Now there is no dampening, as you can see, no dampening. And what else? You can, let's say, ask to record all the result for your sensor, which is the same sensor on the locations as we have predefined, to record all the, let's say, result on these locations. What else we have to know is simply going to properties. Well, you are simply entering the end time of your simulation as 50 microsecond, 5e minus 4, 6, and then the first time increment, 1e minus 6, and maximum 5e minus 5. Where it's coming from, again back to what we had done on the testing about mass participation. All right, I can show you a result. All right, so it is linear dynamic study. I have considered my camera with initial condition and fixed. What I have requested is up to 10 frequencies, and if I look at the result, let's say run this study, it's going to mesh, it's going to run, and then I can check for my mass participation. All right, so solving the model here in linear dynamic, we can look at the, let's say, mass participation and natural frequencies. All right, so it is going to solve very quickly, and then we will have the results. Okay, so just recording it, and now the results should be updated in very soon. All right, so all nearly done and finished, and let's have a look. Here is our result section, and simply we can have a look to list resonant frequencies. Well, you can see from the first mode to the 10th mode about the frequency radian per second, hertz, and the period is occurring. In order to accept or pick up any of this, as we said, the first one is looking at the frequency. Anything around 5,000-6,000 is hardly to imagine to, let's say, occur. Therefore, I'm picking up this time for my initial time and recording time steps divided by 10. Well, beforehand, we have to go and list the mass participation. Requesting for 10, you can see X direction, Y direction, and Z direction, we have around 80% of the mass participation from all components. So that is assuring that we are capturing all the components participation into the vibration in all three, let's say, direction. And then since we have achieved that, we going and right-clicking and looking at the resonant frequencies, and we taking the time divided by 10, as you would like to have a very conservative approach. and spending a lot of time, or more, let's say, relaxed approach, which is taking that time. So it is 1e minus 4, and what we have set up on no dampening here, you can see I have put a very tiny time step to, let's say, create the stress on the model, and just recording 5e minus 5 on my system. All right, so the rest is about your advanced option, which is using the force control and the other factors for eliminating singularities, your convergence tolerance, and maximum iteration if you like to set it. All right, so from this point, the nonlinear study is ready to perform. Looking at the result, stress values are simply here being recorded, and we can see the reality of them. All right, so looking at our stress, and you can see I can go edit definition and just looking at my specific components. So on the selected entities, and this body is what we are interested on seeing the values, and then pin this, clicking OK, and we are getting this. Make sure you are simply showing min and max on the parts only, and here it is. That's what we have as the stress distribution on this component. Let me hide this fixture, and that is yes. Well, similar trend, we have impact stress singularities here in this camera. Looking at the displacements, we are talking about hitting to the target and stress propagation through our model. So that since the file is pretty heavy, it's trying to build up the animation very soon, and let it start its work. So yeah, definitely we do have different magnitude of displacement or deformation in different area, and then simply we can let's say trace those magnitude. It's showing us around 0.39 to a very zero let's say displacement on here. So that small almost look like deformation on our structure. Let me stop this, and that is not really helpful. Look at the stress values, and again we can see a very high stress value. That is really comparable with what we have achieved in let's say drop test. Very high stress concentration here, and very big magnitude of stress because we have no dampening, we have super stiff let's say target, and we have very short time of impact. Now let's look at the response graph. The response graph also showing us a very high magnitude of stress. Well, the same node and high value up to 500. The average high, we have the average, let's say, top stress or peak stress we have achieved is around 400 for the other nodes in here. Okay, now we have set up our nonlinear dynamic studies. We brought the participation from the other, let's say, sectors, from, let's say, performing a linear dynamic studies, and we record our result in a correct sort of a scheme. Now let's go and create the second case, which this time what I would like to introduce here is same contact set here, same initial condition, and same mesh gravity and parts. Well, this time I do have a Rayleigh dampening active. The alpha beta values are coming. However, plane is out of the scope of this presentation, and again we can let's say assist you to find more information if you like. So alpha times mass matrix, beta times stiffness matrix. That is how the Rayleigh dampening is introducing. We record all the results for the sensor, and now let's have a look to the stress values. So simply looking at here to the stress, well, the dampening is being accounted, we can see a huge decrease on the top stress value. around from 1900 megapascal down to 1300 megapascal. Well, the same distribution you can see, it is showing us the peaks and stress singularities and also displacement here. Similarly, we have the response graph, which is showing us much smoother increase and decrease through these von Mises stress peak values. So it means there is a factor which is dissipating energy and filter the vibration for us. You can see this graph. Now let's make the case as close to the reality. Well, I'm considering not only dampening, but also plasticities on top cover, bottom cover, and alloy steel here. Sorry, not on alloy steel, for the camera's components. All right, with that one, if we look at the result, then we see a very interesting figure here. Updating the stress results, and this time we can see, first of all, as we expecting, since these are two separated components, as the contact set you can see, we have reduced the magnitude of stress and we are developing high stress in contact. So this case study is considering not only plasticity, but also the local stress magnification here, as we have assembly, as well as we do have dampening. Dampening, assembly, and also plasticity. All these factors is showing us a much more accurate result and more close to the reality stress, what is really happening. Now, as a designer, you can have your judgment truly if the material is failing, the camera is broken, lens area has any major impact or not based on this response graph. Much reduction in the top values of stress. Alrighty, so with that one, let's have a look to the case comparison we have here and have a look here. If we have bounded and no dampening in a nonlinear case, we're recording high values of stress, but significantly, if we're considering dampening, we are reducing the top stress value by 59%. And if we're considering the dampening, the material plasticity, and also nonlinearities of the geometry or contact dampening as well, we're coming to the last figure, which we have 80% reduction in our top stress values in a lens area. So that's simply telling us, as a designer, first of all, we have to understand the correct, let's say, physical problem, then trying to translate everything in a correct order and try to close our estimation and assumption to the reality. All right, so if you need more information about this product, the Simulation Premium Nonlinear Dynamic, which is the most accurate one to capture your occlusion, please contact me for technical information. So I'm Svandyar Kuhi. Or if you need to have a more commercial discussion, please contact John Belsham, which is Simulation Product Manager at Intercad. I would like to thank everybody for attendance and listening, and we are happy to take and answer your offline calls at any time you like. Thank you so much, and hope to see you in the next webinar.